It says for each of the following equations, determine which of the following statements are true. 1. For every real number x, there exists a real number y such the equation is true. And 2. There exists a real number x such that for every real number y, the equation is true. Note that it is possible for both statements to be true or for both to be false. So this is great practice with double quantifiers. We'll start with 2x plus y equals 7. Is it true that for every real number x, we can find some number y that makes this equation true? So if we pick x, we just need to find y, but y can be dependent on whatever x that we choose. So for example, if we pick x equals 1, we would pick y equals 5, so that 2x plus y equals 7. If we pick x equals 3, then we would pick y equals 1. And so in general, whatever my x is, I want my y to be 7 minus 2x. And 7 minus 2x is always going to be a real number. So yes, for any real number you give me, I can find another real number by doing 7 minus 2 times whatever that number x is, and that will make 2x plus y equals 7 true. So 1 is true. Now let's look at 2. So there exists a real number x such that for every real number y, the equation is true. Now that's definitely false, but let's see why that is. Let's say we pick x equals 0. Well, then that means y must equal 7 in order for part A to be true. But if we pick y equals 6, then part A is false. So that means when we pick x equals 0, then it is certainly not true that for all y, including y equals 6, part A is true. But this could be because we picked the wrong x. Keep in mind that part 2 says there exists a real number x. Maybe we didn't pick the right one. But it doesn't really matter. If we pick x equals 10, for example, no matter what we pick, y is going to be automatically determined by the formula y equals 7 minus 2x, which in this case is negative 13. So y equals negative 12 would make part A false. So certainly for x equals 10, the statement is not true for all y. It's only true for one specific y. And so that's why part 2 is false. It doesn't really matter what we pick for x. This is always going to be the same kind of reasoning. For part B, this says for all real number x, there exists a real number y that makes this equation true. And in general, we can pick y equals 0, regardless of what x is, and part B will be true. So for every x value, we'll just pick y equals 0, and part B is true. For the second one, there exists a real number x such that for every real number y, the equation is true. The answer here is this is also true because we can pick a very special x value, 0. Part 2 is making a claim about the existence of a number, and here I am showing you that existence. X equals 0 is the special x value that makes it so that for every real number y, y plus 0 equals 0 plus y. That's true. So part 2 is true. Now you could have picked x equals 0, but you could have also picked x equals 5 to justify why this part 2 is still true. But to prove that an existentially quantified statement is true, you only need to provide one example. Part C says x squared minus 2xy plus y squared equals 0. So part 1 is making a claim about any real number x. So let's pick a random number like x equals 3. And now we have to ask ourselves, is there a real number y that makes this equation true? So we have 9 minus 6y plus y squared equals 0. Well, in this case, we can pick y equals 3, and we found the existence of a y value for this particular x value that makes the equation true. But that's because we picked x equals 3. This statement has to be true for all x. Now, if you notice, this is a quadratic equation, and so the solutions for y are going to be y equals negative b plus or minus the square root of b squared, which is 4x squared, minus 4ac, which is 4x squared. And keep in mind, we're doing the quadratic formula where y is the unknown and x is just a fixed constant. And this is all over 2a, which is 2x squared. What's important here is that my discriminant here is 0, which means that there will always be a solution in the real numbers. So for any x value, I can find a y value that makes this work no matter what. So that's why 1 is true. For part 2, this says there exists a real number x such that for every real number y, the equation is true. The problem here is that this is a parabola, and a parabola is never just going to be on the x-axis for every value y. So when we pick our x value, we're going to get specifically a parabola, and that parabola is not going to just be the x-axis. It's going to be a parabola. And there's a difference between a parabola and the x-axis. They're just never the same shape. So the question then is there an x value that we can make this equation simpler than a parabola? And the answer is no. No matter what x value you pick, this is going to be a parabola. So no matter what, 2 is going to be false. There does not exist a real number that makes it so that the output of this parabola is always 0, regardless of what y value I pick. Now let's do part D. For every real number x, there exists a real number y such that the equation is true. I would say that's true because we can always pick a very special y value, y equals 1. Regardless of what you pick for your x value, y equals 1 is going to make the product 0 based on the zero product principle. Part 2 says there exists a real number x such that for every real number y, the equation is true. This is also true because we can pick a very special number x equals 5, and now it doesn't matter what you pick for y, 5 minus 5 is 0, and so the product is going to be 0. For part E, x squared plus y squared equals negative 1. For every real number x, there exists a real number y. So in this case, I would say 1 is false. Number 1 is saying for all real numbers x. So we should be able to pick any x value, and then we should be able to find a y value that makes this true. But if we pick x equals 0 specifically, then there is no y value that's real such that y squared equals negative 1. So in order for number 1 to be true for all x, then it has to be true for this specific x. And it's not true for this specific x, so 1 is false. For 2, there exists a real number x such that for every real number y, the equation is true. This is also false because it doesn't matter what you pick for x. No matter what, you're going to get y squared equals something negative. Because whatever you pick for x, x squared is going to be positive. And so to move x squared to the right-hand side, we have to subtract a positive number. And if you take a negative number and you subtract a positive number, you're going to get a negative number, and this can never happen. So that's why 2 is false. Thanks, everyone, and I'll see you in the next video.